Unlike alkyl halides, aryl halides do not undergo standard SN2 reactions because the aromatic ring blocks backside attack and the carbon-halogen bond is exceptionally strong. Today, we explore the unique benzyne pathway that allows substitution to occur under strong basic conditions. To overcome the stability of the benzene ring, we require extremely strong bases like sodium amide or high temperatures. These conditions trigger a specialized elimination-addition sequence rather than a direct displacement, leading to fascinating structural outcomes. The mechanism begins with the strong base abstracting a proton from the position adjacent to the leaving group. This creates a carbanion intermediate, setting the stage for the formation of a highly reactive and unstable species. As the electrons from the carbanion shift to form a new bond, the halide leaving group is expelled. This creates benzyne, a neutral but highly strained intermediate featuring a formal triple bond within the six-membered ring. This triple bond is not like a standard alkyne. It results from the sideways overlap of sp2 orbitals in the plane of the ring. Because these orbitals are poorly aligned, the bond is very weak and the molecule is incredibly reactive. Because the benzyne intermediate is often symmetrical, the nucleophile can attack either carbon of the triple bond. This is a crucial detail that explains why we often see multiple product isomers in these reactions. Evidence for this mechanism comes from isotopic labeling. If we label the carbon attached to the chlorine, we find the incoming nucleophile ends up on both the labeled carbon and the adjacent carbon in roughly equal amounts. After the nucleophile attacks, the resulting aryl anion is highly basic. It quickly abstracts a proton from the solvent, such as ammonia, to regenerate the aromatic system and complete the substitution process. Consider orthobromotoluene. After the bromine leaves, the triple bond forms between carbons 1 and 2. The nucleophile can then attack either position, potentially yielding both ortho and metatoluene products. When the nucleophile attaches to a position different from where the leaving group was, it is called synesubstitution. In this case, the methyl group's inductive effect is minimal, leading to a nearly even mix of isomers. Substituents already on the ring can influence where the nucleophile attacks. Strong electron-withdrawing groups, like trifluoromethyl, stabilize the negative charge in the transition state, directing the nucleophile to specific positions. The nucleophile prefers to attack the carbon that places the resulting negative charge closer to the electron-withdrawing group. This electrostatic stabilization dictates the major product in substituted benzyne reactions. It is important to distinguish this from the SNR mechanism. SNR requires strong electron-withdrawing groups like nitro groups to stabilize a Mesenheimer complex, whereas the benzyne mechanism relies on strong bases and elimination. To summarize, the benzyne mechanism involves a four-step process. We eliminate a proton and a halide to form a strained triple bond, add a nucleophile, and finally protonate to reach the stable product. Remember that benzyne is a neutral, highly reactive intermediate. Its formation explains why substitution can occur at positions adjacent to the original halogen, a result impossible via standard substitution pathways. Let's test your knowledge. If we start with parachlorotoluene, the triple bond forms between the para and meta positions. Because of the symmetry of the benzyne intermediate, how many distinct products will result? The answer is 2. The nucleophile attacks either end of the triple bond, yielding a mixture of meta and para isomers. Thank you for joining this deep dive into organic mechanisms. Generated by Vision Solve AI.